Hello everyone, I'm Muhammad Dishan. So today I'm going to explain basically dance population code, the review of it, and kind of a quick tutorial like how to run this code and for the population inference using the gravitational wave public data and how you can modify it basically. So let's start with it. So I will start from very basic, like quick review of the binary and their parameters, and then I will explain like how many events we have till now, like the published O3 events, DWT3, and then I will explain the method about the population inference, uh, theoretical one, and then I will move to the coding part. I will actually show you like how to use the code to make the inference and how can tweak you can tweak the model. You can build your own model using the dance code to make your own inference for your research, and then I will explain like what are my personal future goals related to this code. Yeah. So let's start with very basic, quick review for the ones like who do not know. Although it will not be cover the very basic of the stuff, but that's the things that I feel like they are important to discuss at the beginning. So that's what I'm going to explain over here. So if we will start, so if you can see that I have the image of the binary. So that is the first black hole. That is the second black hole. So the mass of that black hole will be m1, and that mass of this one would be m2. So we will represent it mass of these two black holes with m1 or m2, and s1 is basically the spin magnitude of those black holes because they will be spinning and coalescing around each other. So we will consider their mass and then we will consider their spin. So s1, or even sometimes we denote it with a1 and a2, so do not get confused. A1 or a2, s1 or s2, we use them for the spin magnitude, and m1 and m2, they are the masses of the black hole, and l is the basically angular momentum of the orbit, and S1 and S2 for the same for the spins. And this one is a very simple version, and that is the like little bit modified one. Like if you have a precessing binary, and if you have a kind of a tilt in your black holes, their spin, like in the left hand side s1 s2, if you look at the vectors, they are exactly aligned with the angular momentum. They are parallel to each other, like s1 s2 and l2, they are parallel. So we call it a aligned spin case. That is the very simplified version of this binaries. But if you look at the right hand side, so that spin vector is not exactly aligned with the total angular momentum denoted by the j. It has some angle, we call it tilt. And in if you look at, if I will explain further, like if you look at the data points, so do we have a cos tilt that we use for the to represent that the theta one, that angle, that is the spin makes with the basically with the angular momentum. So yes, so we do have a processing binaries, and their alignment is not always aligned. It can be misaligned, can be anti-aligned. So we use the theta angle and we call it cos tilt in our parameter estimation file. So I will explain it there. So for the sake of simplicity and just for a intro, you just keep in mind that you have the mass of those black holes, two black holes. We call them as a binary, as a whole, and you have the spin, their individual spins, and you have the total angular momentum. And theta jn is basically, let's say we have observer over here. So the angle that we make with the total angular momentum and with the line of sight, that is called theta jn over here, or we call it angle of inclination. And yes, so these are the things that you should know about the binary, very basic things. I will not go in more technical details. So yeah, mass and spin, and the third important one is like the orbit. If the orbit is circular, so we call it circular orbit. Like if, and we also have an eccentric orbit. So if you look at this shape of this orbit, it's not a circle, so it is eccentric orbit. So yeah, I also study about the orbit. So yeah, eccentricity is another parameter that we will study. Okay. So yeah, let's move forward. So we have, you have the basic idea of the binary. So we have the binary somewhere in the space, and the LIGO, Virgo, and Cagra, they are detectors. They detect those binaries. How they detect it? Like when they coalesce, they produce gravitational waves, and the LIGO detect those gravitational waves, and we infer the properties of those binaries from those gravitational waves. And based on those gravitational waves and their data, basically, we have this is the grave. We call it graveyard because black holes forms when the star died. So the blue dot in this figure, like the first one, the blue over here, that is the primary, like the M2 black hole, and this is the M1 black hole, because M1 is always we denote with the whatever the higher mass, that is the primary black hole, and whatever the lower mass black hole, we call it secondary. So we call it M2 for the lower mass, M1 is for the always higher mass. So when these two black hole merge, so they produce the additional, they produce the final black hole. Like when these two of them merge, we get the final output of the black hole over here. So that's why you see the arrows over here. These two are the basically that gives to the birth to the final black hole, and that is heavier than the previous two. Like you can their parents black hole. So yeah, these are the final black hole after the merger, and you can see their masses over here, and their mass is around 100, and the maximum mass after the merger goes to the 200. But before the merger, you can see that the most of the black hole are below the 50, basically, most of them. But we do have more than 50 as well. They're like around 100. The maximum mass we get till now is around 100. But after merger, it definitely goes to the 100 plus. So yeah, these are the black holes that detected by the LIGO. And they we do have a other mass of the black hole. They are not detected by the LIGO. It's the technical detail, like the sensitivity range of the LIGO. So that's why we are able to detect black hole in that particular mass spectrum. But the black hole with different size, they do exist. We do have a supermassive black holes as well. So, but for the sake of our research interest right now, we will just focus on these blue ones. Okay, so the purpose to show that, like, we have till the public data, the O3 data, we have around 90 confirmed detection of the LIGO. They are published, and we can use that data to infer the overall population of such binaries in the universe. Like, what can be the minimum mass, what can be the maximum mass, what can be the merger rate that we can detect in our detectors. So we infer to such kind of information using those existing mergers. So, what is actually the population inference? Like we have the individual detections. So, based on those individual detection, how we infer the overall population of such binaries. So, this is kind of a schematic diagram, like the ingredients that we need. So, the first of all, we need data. So, we have the publicly available data for the 90 events. Okay, even for the sake of research, you can make your fake PE is for parameter estimation, like the parameters of the binary, like mass, spin. We can generate fake with some models, and we can add error in them. But we do have the 90 real events, and in the future O4 run that is running right now. So definitely, we will have hundreds of more events in future. So we will have a significant amount of data in future based on the LIGO sensitivity. But the thing is that we need data, and we have it, either fake, either real or real. And what this data have, this in this data we will have the masses of those binaries, M1, M2. We will have the spin, we have the cos tilt. If there is eccentricity, we have. But right now we do not have eccentricity in the real events because we are not detecting them. We do not. There are some other technical detail like why we do not have eccentricity, but yet we do not have eccentricity in real events. So to make the eccentric inference, we always need the fake PEs that we generate to verify our models with the eccentricity, and Z for the redshift. So we have such information from the individual events. Once you have a data, then you need a population model. And the population model, that is a technical thing. Like we build basically population model based on the mass, spin, redshift, and eccentricity distribution. Like for the each parameter, we have different distributions. We combine them, and that combination makes a single model. and we call it the building a model process. I will explain it later in for the slides, but keep in mind mass, spin, redshift, eccentricity, they have their own separate distribution, and we combine them and we build the model. So there is a pure theoretical work in the backend, but we do have the models. So once you have the model, and we do not know which one is the true model, so we try to constrain the model parameter based on the data we have. So for this, we need a Bayesian inference, and in the Bayesian inference, you need that basically prior, likelihood, and posteriors. That's what we calculate. Prior, we provide basically that. I will not go into the detail. I hope you guys know about it because this is not an introductory tutorial. So that's for the scientists. So the we need prior, likelihood, posterior, and what we get from there, we get the minimum, maximum mass, eccentricity distribution, maximum spin, and spin distribution. R is for the merger rate. So based on the individual events, we try to infer the overall population parameters, like what can be the minimum max of the black hole or the neutron stars in the universe, what can be the maximum mass, and what can be the maximum eccentricity distribution we can get from there. Same for the spin as well. So we try to get the idea of the overall population of those compact binaries in the universe. So this is the main thing that we are trying to do. So how we do it? So the first thing that we need data. So how you can get the data? You can just simply, the easiest way to go to the Zenido website. Here is the link, and you can use that link, and it has all the data, and you can use that data. You can download that data basically from there, and that data normally has the h5 file format. Okay, .h5 file format, and in that file format you can go to the my hdfi website, and you can just view that file, and it will have that columns in the posterior samples that what we use basically. Not all of them, just go into the posterior sample, and you will use the A1 spin, A2 spin. We need them. I can show you over here as well. Like if you go to the website, so this one is like if you go to the posterior, if you open the file, so you will have the different waveforms uh, that they use for the parameter estimation. So we usually, for the over inference, we use the mixed one at the end. In the posterior samples, we get the all the information, like they have all the parameter, but we are interested in mass and mass one and the cos tilt. Same for the mass two, A1, A2. So we need those values. So okay. So but the point to show that, like when you go to the Zeneto website, that's what I was showing you. The link is there in the presentation. So if you open that page, so they have all the tutorials over here, like how you can download. You can use the pip to download all of the data in that website, and you can use this Jupyter notebook to view that data, and they make them inference about that. But the data files that you need, they are over here. The non-Cosmo and Cosmos, you need the Cosmo.h5 file for the each event. If you look at this event, so that is they're separate events, and they have a each file for each event. So you need to download all of them, or whatever the events you need to make your inference. Okay. So this is, if you look at the like the way they have written these names, this is the time. You can read the reverse order. The the last one is the time, and this one is the date, like 09, 11 is the month, 9 is the date, 11 is the month, and 19 is the year, like 9 November 2019. So all of the events are here. You can download each separate event, or as a whole event. But once you get download it, you can view it over here, but technically you do not need it to view to this file, but to get the idea like what is in that file and what the data points you need. So in that file, you just need, if you go to the in the mix waveform model, and you just need the posterior sample, and to run the population inference, you just need mass, A, and spin components from this. Okay. So I will explain it how you do it, but that is the one perspective like how to get the data. Okay, so I assume like at that stage you know how to download the data and you can view the data like what's in the .h5 format. But the thing is that to run the dance code for the population inference, you cannot use this h5 file. Okay, the way the dan code is written, you need the text file. So Dan has written the Python script that is in the Dan's code. I will show it to you. But you can run that script, and this the h5 file will convert it into the text file, and it will just store the those columns which are required to run the code, like the masses of those binaries, spin, and their tilt. That's all you need to run the inference in the dance code. So we will use them. So I will show you the script there how to convert it, and then second stage, you have the data, you have converted it into the text file that can be used for the in the dance code. Now you can use the now you need a population model. So the thing I was trying to explain, like for the mass, for the M1 or M2, you have a power law model. Okay, and in that you will give this model m1 and m2 that is in the text file over here, like m1 and m2, and it will give you the as output. It will constrain m mean and m max and alpha m etc. And same for the spin, you need to provide the spin component. It will constrain the maximum spin and etc. And same for the eccentricity, you will provide the eccentricity value and it will constrain the sigma eccentricity from it. And in the redshift, it will constrain the k basically. So for each parameter, you have the different distribution, and you will combine them in this way to build a population model. Like this is the general term. If you expand it, the W is for the weighting, and you have to give the distribution for the mass, then the spin, eccentricity, and redshift. You can even give just math. You can use mass and spin, or you can use mass, spin, eccentricity. It's totally depend on you, but you have to combine those terms in a way like to build a whole population model. Like in my case, I am using the eccentricity, so that's why I need to add the eccentricity distribution as well. But if you do not want to use eccentricity, just simply combine the mass and spin model distribution basically and build your own model. And so that is the part that dance code handles very well. Like it can the whatever the models he define in his code, you can use those models and you can combine them and to build a different model from it and make a inference on that particular model. So I will explain it like how the coding part but is done in the inference. Okay, now you have a data, you have built the model. So now you just need to run the code to make the population inference. So in the population inference, the important part is you find the likelihood, and that is the integral that we need to calculate to find the likelihood. And for the likelihood, the LNY, the cap is the small lambda over here. That is the likelihood of the in each individual event. R is the rate, and that is again probability of small lambda, like the individual event given the population parameter capital lambda. Keep in mind, capital lambda is the they are the parameters of the population, like m mean, m max, and rate etc. And the small lambda is the parameter of the individual event, like m1, m2, a1, a2, and mu is the expected number of events. So we use this Poisson likelihood to um, to compute our likelihood basically. And then we will provide the priors, and we will use we provide prior and likelihood we will compute over posterior. So to compute this posterior, we will use the MC method. That is already like this is the sampler method from the and that is defined the EMCEE package, Python package. So the dance code basically written on the Python, and it used the EMCEE module to run the MCMC sampler in it. So we have all of those three things, and last of that, LVK sensitivity. Like we need we do have the model, we have a data, but our LIGO, Virgo, and Kagra, those detectors, they have a sensitivity for particular mass range and particular volume of the sky, and they run for some certain time. So we have to account all of this, so to get the accurate inference. So we use this um, integral to account for the sensitivity of the instrument, and we do the weighting stuff using this integral, and then has calculated that integral in the vt.py file that is already given, and that will basically include the that will just basically compute the sensitivity. If you want to read the technical details, so you can just go into the link, and that is the dance original paper published in 2019 that have all the detail about the how did he compute this VT file. Okay, so again, like whatever the schematic I've explained it to you, now I will show it to you with the help of the code. So just a quick overview, then I will actually do the tutorial type thing. So if you go to the dance code, so in the source directory, that is one of the main major directory in the source directory, mm, we need to build the model. Okay, so to build a model, basically what he did, like in the building block, if you go into the source pop models, then you have to go to the astro model, and you have the building block. Basically in the pop model you have a building block, and in the building block he basically defined all of the models for the spin and mass, like power law model, eccentricity model, not eccentricity, power law and spin, like trunk norm, power law, Gaussian mass, broken power law, beta conditional. So he defined all of the models, or you can say all of the distribution over here for mass and spin in the building block. And in the application folder, in the BBH, he basically uh, build the model over here. Like he defined individual distribution in the building block, and he used those individual distribution in the application folder in the population.py file to build the model. So he is actually building the model in population.py file. So if you look, if you see at this mixture power law Gaussian, so in the population.py he basically imported three different models. Like he imported Gaussian mass, power law for the mass, trunk norm, and the beta distribution. So he basically imported four different distribution: beta, trunk norm, power law, and Gaussian for the mass. Okay, so trunk norm and the beta, they both are for the spin, and Gaussian and power law, they both are for the masses. So he used these four different distribution to build a model with spin in the population.py. And then this the like he when you have the model to run the Bayesian inference, you need the prior and for the likelihood everything. So he defined those things in this repo for the plotting thing and everything, like how to plot different mass distribution, spin distribution. And the next part is to run that code. So we do have the run directory over there, and thankfully Dan has made the bash script file over there, and you just need to run the bash script. But I will explain it later. When you run this run.mcmc.s bash script, it does have, it basically call that file main.py, and then this file will use all the priors and everything, like what are the prior and constant you are given over here in a JSON file. It will use that the main.py file. So you can simply run this bash script, and it will use that vt.hdf file and all the prior and constant that you are given over here, and it will run that main.py file, and it will make the inference of this particular population model that you have defined. So that was the that's kind of a layout. Now we can move to the actual coding. Like I will show you like how to do the coding part, and ultimately you will get some kind of a plots, like the Dan code automatically it has the scripts to make the plot. So let me go to the coding part now. Okay, so we have the code here. So first of all, you need these two repos. Okay, very first. like if you go to this repo, I will give you the link at the end of the slide. So if you go, this repo has a very good tutorial. It has written everything over here. So if you just follow it, follow the instruction in that readme file, okay, so you can just simply, the first step is like, okay, let me just do it. The first step is just git clone it, okay. So let me do it over here. I will provide the link for this one. So just copy this one over here, and you can simply clone here. Let's say git clone, and this one, let's say I'm going to name it tutorial, but it doesn't matter you want to name it or not. So you can clone it with the actual name it has. So I'm just trying to give a demo, so that's why I did this tutorial. Okay, so if you go to the tutorial, so you have the virtual environment, okay. So I am just going to remove it so I can create new one. So Python minus m vnv and vnv, the last, this vnv, the last one, you can call it that, the name of the environment can be anything. I just say, let's say environment of the tutorial, okay. So I have created the virtual environment. So you can see the all of the guidelines here, they are provided here. Like if you go into the read my file, so he gave you the all of the instruction like how to create the virtual environment. So you can follow this one, or if you follow along the video, because I just remember it, so I can just do it over here. So you have the virtual environment. So if you have the virtual environment, so now you need to activate it. I just deactivated previous one, but your environment is over here right now, environment tutorial. So I'm just going to activate it. So source environment bin and activate. So your environment has been activated, okay. So now you have to git clone the other repo, okay. You have that the actual code basically. So this code is over here, this is the dance code, actual code. So I can you can just git clone this one over here from git and clone. So this is the totally different code. This is called, this is called Bayesian parametric population model. I will give the link for this one, so you can just git clone this one as well. So let's say git, sorry, git clone this, and I'm again going to rename it pop models and cloning over here. Okay, so the cloning is done. Okay, so you have everything over here. Okay, so this is the pop models that have everything, even the source file that I was explaining previously in a structure that is over here. So what you need to do, you need to install it in this one. Okay, so in that environment, so the very first thing, mm, I'm going to switch the branch, but you do not need to do it, because once you will watch that video, so there are some minor changes that I have made that they will be into the master branch. So just keep in the master branch. And now I just need to install wheel first. Yes, and then I need to okay, I have installed the and now you just need pip install and dot. Okay, but keep in mind pip install dot is should be there wherever you have a setup.py, because it will read it. Okay, so installation is done. So you can check it, pop. Yeah, so if you do it pop, so whatever the built-in commands it should have in here, and you can do this to make sure it is properly installed minus that. So okay, so it gives me the error, it means to say there is some issue. So there are quick fix. You just need to deactivate your Python environment and just simply reactivate it. And if you to again activate it, you need to go to source, environment, bin, and activate. So if you activate it, so now I can do the pop models binary black hole mixture gauss minus h. Yeah, it seems like, yeah. So now it is working. So you can say that, like, you can see the documentation. So once you see the documentation, it means your package is properly installed in it. So now you are good to go and play with that code. It's properly installed. And now to run it, you just need to go to the run directory, and over here you choose your own model, and you can just run that file. Okay, like dot slash run, sorry, dot slash run mcmc dot sh. Okay, but it will not work. It will not work right now because if I run it, let's say dot slash run mcmc sh, so we do not have the data file, so it will give you the error. But you can see that it just finished without showing you any error, because if you go into the run sh, let's say if I'll open the run sh file, so vi run sh, so in the sh file you can see that the output is getting stored in the logs file. So if you really want to quickly see your output, so you can just comment it for a, so you're not here at the beginning, so you can just comment it for a moment to see what a type of the error you are getting and what is the problem over here, over there. So I'm just going to run it. So now you will, yeah. So what did it set? Samples dot gwtc not found, because we do not have a data. So the way I told you, you have to go to the Zeneto website or any other, whatever the way you are comfortable with. You have to download the data, and that downloaded data should be in this data folder. Okay, CD data, and you need to store your HDF files in here. CD HDF files. So this is where you will store all of your H5 files, and once you go to, and then you have to go to the bin, and you have to you have to run this script, convert hdf file to text.py. So it will basically convert those h5 files to the text file. Okay, so you will convert them into the text file, so this they will show up here. Okay, they will show up here. So once they will show up here, uh, you are good to go. Okay, so for the sake of simplicity, let me just um, uh, copy something, so copy any file maybe I will have previously from somewhere else. So we can use this, um, yeah, we can use this one. Yeah, any file igw. Okay, so I am just going to copy one file. So you can see that we have one .dat file. So if you have the text file, so now your code should run properly. If you go to the run file, oh sorry, not cd runs cd multi source, and you have to run this script again. Okay, dot slash run. Okay, now what is the problem? I can explain it to you, because I have, if you I will open, if I'll open this file, let's say open run mcmcsh. So over here in this row I have defined like the all of the file formats, but they are not here. Okay, so you have to give the path where is your actual data has been stored, and it is already here. So there are various ways. The one of the fix you can do it, like you can go to the text file. Okay, so whatever the file over here, so you can give the whole path. Okay, whole path over here in this file. So here is the complete path, and whatever I'm going to say, like whatever the um, text file are there, the script will run from there. So now I will go back, runs. You should go to the run multi-source, and now you can run it. I hope it will, finger cross, it will not give me the error because I have given them the exact path, like where you can read the file. Yes. So yeah, so once you see such kind of a warning, it means to say your code is running fine. These are the some, yeah. If you reach that stage, it means to say your code is running fine. You are good to go. You are going fine. Everything would be okay. You have to wait. It depends on the processor speed. It will take a long time. So I just have one file, so it will finish quickly. But I'm just going to abort it over here just to show you like how it works. And once the run is finished, and once the run is finished, you have to run the post processing file. Okay, so what it will do, like whatever the files it will create, it will just make their plots over here. Okay, so once you run the post processing, you will see such kind of plots. Okay, so once you run the post processing, so you should see such plots. These are the chain plots to see the like how the MCMC is converging, and that is the important plot that shows the rates, and even for different events, different subpopulations, you will see that such kind of a plots. So once you get there, you can say that your run is fine. Okay, so that was all about how to run it. Okay, so other than running, the next thing is like how to modify it for your any certain model. Like that is the, like if you go in the runs directly, it has already defined the code whatever you want to run. So now we will go to the modification part, like how you can modify it. So just quickly, I'm going to show you over here. Let's say if you go into the in this file, if you go to the what you say, yeah, into the source code, in the source directory, pop models, application, and bbh. If you go to the bbh, so these are the different directories. Okay, you can say that like we have a different directories over here. um, a broken power law, mixture power law, O2 model. So this is where he's actually building a model, like the concept that I explained you, like to build a model. So this is where it is actually building the model. So if you go to into one of the directory, let's say I'll go into the mixture power law, and the important file for you if you want to like easily want to do your stuff and get your results, so you have to open this population.py file. Okay, so that is the file that is already open over here. So what it's doing over here, like this whole file is basically doing the building model thing. So in the building blocks, like in the pop models, astro model, and the building block directory, he defined the power law model, and he's importing it over here. Then he defined the different power law models. So he's importing the power law model, and then he's importing the Gaussian mass model. Okay, so they both are for the masses. And these two are for the spins that he imported. So he imported basically four different models over here. That is the thing that I was trying to explain. Yes, so we have the four different models, and uh, we are building the model. So that thing it is doing in that file population.py. So you have to he imported four different models, and then this file, this section, that is basically transforming the coordinates to make to like everything should run smoothly and they should have the same coordinates. So that is the m1 mass for the, and that is for the mass 2, and chi is for the spin, and cos tilt is if you have a misaligned spin, then you need a cos tilt as well. So then he defined the get spin, and in the get spin basically you have the beta population, like the beta distribution, and he use this beta distribution for the spin 1 and spin 2, and then population cos 1 is for the cos tilt basically. So he used the tilt. He's getting the tilt from there, from the trunk norm population. So the tilt part is from the trunk norm population, and the magnitude from part this for is from the beta distribution, and then we have the complete distribution at the end, with the tilt. And now in the defined Gaussian part, he is basically getting the different mass distribution, and he has two different distribution for the mass, that like the Gaussian one and the power law. So he used those terms to get the masses, and ultimately in the get population, he basically combining the mass and the spin to get the whole population model, and he's returning it after mixing the whole model at the end. So if you want to use any other distribution, you can import it here, and you have to modify that code in that in over here to get your own population. Okay, I will show you the one of the modification that I did. And yeah, that is the main file. Like when you do the dot run mcmc asset script, so it is basically really calling that file main.py. Okay, and that file is in the pop model application bbh, like wherever you have the population, like you have the you are building the model, you have the population.p file. This directly also have the main.py file. So if you are running for some certain model, so it will have its own main.py file that will um, run actually. Okay, and that's what we are doing over here. Like when we call this pop models bbh power law gauss, so it basically, that is a built-in command. I can explain you with the setup.p file, like, but basically if you are running the mixture model, like over here in the population py, you have a mixture model, and if you want to run it, so it for this model you have the built-in command, and it will call that main file which is already in the same directory. And how you can build that built-in command if you want to use the same script, so you have to modify the setup.py file, that is in the main directory setup.py file. So you just need to go over here. Yeah, this is where he defined. And the one viewer I was showing it to you, this is one pop model BBH Gaussian, and what it does over here, it go to the pop model directory application BBH mixture, and it's calling the main file. Okay, it's calling it main file. So if you want to build your own model, so what you need to do, you have to create new directory, new folder over here in the application, like same over here in this uh, you have to go over here like pop models application bbh, and these are the different models. So you have to create the new directory. You can just copy paste the mixture model, or you want to create own directory, and you have to give the path over here, and whatever the name you want to give to this entry point, and that will that will be your new built-in command. So you have to change the setup.py file, or if you don't want to do this over here, so you can just simply, what you can do in the run, you have to give the whole path over here. I didn't try that thing, but it may work. Yeah, because it technically that's what this code is doing. So yeah, the main thing is you have to run the main.py file. You can do either way, just leave the whole path over here of that particular file, or you can modify the setup.file or make a key, like the command for to call that particular file, and you need to give all of those parameters. With the double slash, they are optional one, but you must have to give the VT file, priors, and the data files, and the rest of them can take default values as well. Okay, so that's how you modify it. Okay, so that is another example. If I'll give you to you, like if you remember the previous month, it was importing the beta population for the spin, but over here I'm not importing the beta sorry population over here, because I am using the align spin case, and I do not need a trunk node. Okay, um, so what I did, like I can just simply explain to you over here. I think it would be easier. Like for the align spin case, I just need to remove the coast tilt. So wherever I have the coast tilt component, like wherever I have the coast tilt component, I just remove it from everywhere, and the associated distribution from it, and it will give you the aligned spin case. Okay, like everywhere you see the code still, you have to remove it. And like in the get in the if in that in the define get spin, so I don't need um, these two. Okay, so I just need to I can just simply remove that particular part of the course, because I do not need that particular distribution. Okay, so yeah, that's how you modify it. And once you are done your modification in the model and you have built a new repo for the model, now you have to go to the run directory. Okay, you have to go to the run directory, and you have to create a new folder over there to run it. Like for example, if I'll show you in the terminal, finish it everything. So yeah, if you go into the run, like I'm assuming that you have made the modification in the pop models, and now you can go to the runs, and these four different model are the run for the four different models in the backend that are defined in the uh, application, like source model, application, and BBS that defined there. So you do to define, okay, because each model will have that different prior and different coordinate shifts, so you have to handle over here. Like I will go over here, then you will see that you have the let me see the JSON files. Basically, yeah, constants you have, you need to, you may need to modify the constants, you may need to modify the priors over here, because if you change the model, so that particular model will contain some certain priors, so you have to modify the priors as well after changing the model. So yeah, so that is how you modify it. So I think that's what that is all I have to explain about it, about that code. Like but yes, again, it does have some tutorials, it does have some documentation. Yeah, I forgot to mention one thing, like to download the data, the dance tutorial, it does show you the to use the GWT Explorer, but you do not need it because it's not updated. So it will not work, it will show you the error. So use any other way to get the data, but do not get confused with the last part. It does not have to do anything with the code, like the inference part. It that DWT Explorer is just to download the data, and you can download it in either way. Like you can use Zenodo and or any other thing. And yes, yes, and for the plotting thing, you can again you can go to the read my file, and you can see that like you can make the different plot, like in the, you have to just run this bash script in the bin folder, and you will see the some nice colorful plots as well. Okay, thank you, thank you very much. I hope I'm not missing anything, but if still, if you need something, my email would be in the slide, or you can contact me. If you are a LIGO member, you can contact me on a Mattermost, or you can contact me on a Slack. So yeah, so these are some of the links that you need, like to download. Data is here. Tutorial, the repo which has the tutorial, it is here, and the actual the code that do the inference, it is in that link. To view the file, you can use that link. And the code structure, like that is just for the, like if you want to see any code, the flow of that code, so you can use that website and connect it with your existing code. It helps to understand the code. Yeah, thank you very much.